I'm Stefanie Jegelka. I'm a faculty in CSAIL. I work in machine learning. And in this short talk, I'm going to show you a little bit more about our recent work on learning with graphs and combinatorial structures. So to make you understand a little bit better the setup, let's look at some examples. So the first example is learning with graphs. What's a graph? A graph is a structure that consists of entities. Think about people and connections between these entities. Think about friendships or something like that. Another example is a molecule where the entities are atoms in the molecule and the relations are bonds in the molecule. So what are kinds of questions where we want to do machine learning on these things? For example, given a molecule, we would like to predict properties of this molecule, such as will it work as a drug, will it be toxic, things like that. Or another example is that we have interaction networks. So here the entities in this specific example are drugs, and what the connections mean is that there's interactions between these drugs, meaning that if I take these drugs together, I'm actually going to have an adverse side effect, versus if I take them by themselves, they may be okay. So here what we are trying to predict is whether there is actually links in this network, whether there's these relations. So basically, given two drugs, will they have an adverse side effect or not if I take them together? Another example of combinatorial inputs is if my input to my prediction is a collection of items. So think about if you're in a game and you have different treasures, I'm trying to ask the network, the neural network or the machine learning model, what is the largest difference in value between any of the treasures that you see? Or more complex, I'm giving you some setup in a strategy game and you're trying to figure out what is the optimal path that you have to take, what's the optimal strategy to fastest reach from A to B via defeating some little monsters or so. So in both of these setups, what we have is the input is some more complex input, for example, a collection of items or a graph that consists of entities and connections between these entities. So both of these are very relevant machine learning problems. You already see several applications of those. So the question is, how do we do learning with them? So let's first look at the left-hand side. Let's look at learning with graph inputs. So the way this is typically done is with a neural network. And really the key challenge here is, how do I take, say, this molecule, and how do I encode it in a form that I can do learning with it? And here I want to really encode the structure of the relationships or the bonds and other kinds of information I have about the entities in there. So the way this is done is typically with what is called a graph neural network. So a neural network that encodes graphs. And you can think of this neural network actually as a procedure that iterates. So and what it does is it actually computes first the representation or an encoding of every entity or every node in this network, and then of the entire network itself. So think about trying to learn an encoding of that red circle there. You can think of it that is you in a social network, and the blue circles are your friends. So these are the other nodes. So what you do iteratively is that you collect information from your friends and you aggregate that into your representation to get a richer representation of what is actually your neighborhood of friends, the connection of friends. And you do this over and over again, and after a while, what you actually, if you think about it, what has happened is that in each round, your friends have also collected information from their friends. So now if you do this again, you actually get information also from your friends' friends. So sort of the range of information that you get gets larger and larger the longer you go. And once we have done that for a while, what we do is we take all the encodings of all the people in the network and we put them together via various ways into an encoding of the entire network. And that encoding is supposed to characterize the entire structure. So this has been used very effectively on many different tasks. Let me give you another picture that tells you a little bit more how this is related to neural networks. So if you know about neural networks, what you actually may think is that it's sort of this layer-wise thing where you have little computational units and you go from layer to layer and they feed into each other layer and layer and you have a very deep network. So how is this procedure that I just described to you related to neural networks? And to understand this, let's look at the same procedure again and unroll it. So let's say we want an encoding of that yellow circle there, the yellow node. So what you do is you collect information from your neighbors. So these are the three nodes that it's connected to. And those nodes collect information from their neighbors. So now if we unroll this and we have these gray boxes saying that is some operation that takes the information from your neighbors and does something to make it your own representation. So if we unroll this, you get actually a structure that looks like what is called a tree. So you get this wedge-like structure with this branching out that looks like a bit more like a neural network where you have different layers. So the input layer is really your neighbors, a larger neighborhood in the social network, your friends' friends, and they feed into your friends, and your friends feed into you. So now you have actually this layer structure, but it has a very specific wedge shape that's specific to these neural networks. So now the important thing is, what are these gray boxes? How do we actually aggregate that information? And one basic question about these kinds of machine learning models is, well, if I feed it two different graphs, two different social networks, two different molecules, will it actually encode them differently? So why is that a fundamental question? The thing is that if you actually encode them into the same encoding, you cannot distinguish them anymore. So if I predict for one molecule that it's toxic, I necessarily have to say that the other one is toxic too, and maybe that's not true. So what we really want is something that actually can discriminate between different input graphs. So the fundamental question here is, if I give you two different graphs, can you actually distinguish them or not? And when can you and when not? So to think about this problem, let's think about how do we actually, what kind of information do we keep about our graph, about our social network or molecule? So what we actually keep is these little neighborhood structures, these little wedge-like branching out structures. These are the trees. And we essentially encode a graph via a collection of these different trees, one for each node, so one for each person in the network. So when are these sufficient to actually distinguish two graphs? And it turns out actually in very many cases. And there are some special cases when you have lots of symmetries, like these two little graphs in here, where this actually doesn't happen. But in general, you are good. So what we did in our recent research, we exactly characterized what kinds of graphs you can distinguish. And if you look at all possible graphs, that's actually a large amount. But there are failure cases. So it's good, very good to know about them. It's very good to know these kinds of limitations. So now that we know there's like sort of this maximum power of discriminating two different inputs, do you actually ever achieve it? And that actually depends on how you exactly design that neural network. So let's look at a very simple example to sort of think about this a bit more. So let's look at a simple example of a network with 3 or 5 nodes, a graph with 3 or 5 nodes. And we look at what if when we aggregate over our neighbors, we just take the average of the neighbors' information. So think about each of your neighbors having just one number. That's the information you have about the neighbor, 1, 2, or 3. And that's encoded in this picture here. So now let's look at the center node. The center person aggregates the information from the neighbors and averages them. So now what we average is actually a 1 and a 3, which is 2, or we average 2 1s and 2 3s, that's also 2. So just by looking at the averages over the neighbors, there's no way to distinguish between the two different structures. And that actually holds more generally. So there are limitations. And now the question is, how can we make this more discriminative? So what we found is that there's actually a very simple condition that you can phrase mathematically that shows what kinds of operations you can do when you integrate the information from your neighbors that will actually lead to these most discriminative networks. And the way you do this is that you say, if I have a certain set of neighbors as an input, it always has to be a very discriminative encoding. So basically, any inputs of the neighbors, if they are different, any different neighborhoods should lead to different encodings. So is that something that's actually relevant in practice? So I showed you some theoretical considerations. Let's look at a specific example. So here, this is an example learning task where the input is proteins, and we're trying to predict something about the structure of these proteins. And what you would expect is that the richer the model, the more powerful the model, the better it can actually fit the data and make the right predictions on the data we see. So this is what we see here. So from left to right, we have the number of training iterations, so the sort of the learning iterations of our machine learning model. And on the y-axis, what we have is the accuracy, so higher is better. And what we see is the red line, which is sort of the one that satisfies the condition that we pose, that actually gives you the highest accuracy. And if you weaken that, so if you get provably weaker models, you actually see that in the end it's not even learning anything anymore. So this green line sort of lingers and is not actually getting you any accuracy whatsoever. So this is something that is a theoretical result that shows you some fundamental limitations and some fundamental powers. It also gives you some conditions on how you actually design your networks, and that's not only something that's theoretically guaranteed, you actually see the effects in practice too. So to look at a different example, let me briefly sketch another type of learning task to you, and these are reasoning tasks that people have recently started to look at. So the task is as follows, that I give my network a collection of items, so this could be the treasures in a game, or it could be just a collection of shapes, or something more complex, and I ask it questions about this input, about this collection of items, and the neural network has to answer these questions. So I already showed you some examples, like what is the maximum value difference, or what is the color of the furthest objects, or what is the best strategy going through different types of little monsters to actually reach your goal. So in this case, what the neural network actually has to learn, just from the collection of input, it has to basically learn what kind of computational procedure would answer this question. So if you answer this question, you are actually thinking about, well, I do some pairwise comparisons, and then I output some properties of looking at the, doing the pairwise comparisons, looking at the maximum of those, and outputting some properties of those maximum distance objects. So for example, their colors. So you actually do some kind of procedure in your head to answer this question. And what the neural network has to learn is, this is the procedure, these are the steps in the procedure to actually reach to an answer, that on different inputs it can just run this procedure. Now, learning such a computational procedure is actually a very complex thing to do. And the question is, what kinds of neural networks can actually learn this? So there's various ways I could come up with a neural network to learn this. So a simple one would be just take a collection of items, put them next to each other, and feed it into a standard neural network, which is here called a multi-layer perceptron. Another one would be to say, well, if I have the collection of items, if I swap them, that shouldn't really change, say, the distance between the farthest away objects, because it's just the order in which I look at the different shapes. So there should be some invariance, or basically doing a permutation of my inputs shouldn't actually matter. So an architecture that does that is a so-called deep sets architecture. And finally, another one that has even more structure is using a graph neural network. So what in this case you do is you only look at pairwise relations between all possible of your objects, and you do this over and over again. So you already see intuitively that already encodes some kind of looking at pairwise differences, maybe pairwise differences of value or of distance. So now all of these networks in principle can encode the task and can learn it. But if you actually try them in practice, what happens is that from left to right, the networks become actually much better at learning such tasks that I showed you. So the important question is, why does that happen? And does that give us any insight on designing better machine learning models? So what we've actually found is that theoretically and empirically you can actually quantify this. And to make it a little bit informal, what you actually have to think about is, when you answer this question, you are following a computational procedure. You're looking at pairwise differences, you're extracting some information about the argmaxes. So what you do is, you actually do this set of operations. So now if the neural network can actually implement that set of operations by looking at the gray boxes in the network and making them very simple operations, just like a pairwise difference, a maximum of something or so, then actually they can learn the task well. If they basically have to figure out what is actually the structure of the computational procedure, then it becomes much harder for them to learn the task. And following this kind of quantification that you can make formal, what we showed is that these graph neural networks are actually very well suited to learn many of these reasoning tasks that people have recently started to look at, such as looking at basically finding shortest path, or something like looking at physical interactions and trying to predict the future of a physical system and the state of objects that interact, and maybe balls that run into each other. So all of these tasks is something that this kind of neural network is very good at trying to learn. So these were really just two examples from our research that show you that you can have both fundamental results in terms of trying to quantify what can these different machine learning models actually learn and what can they represent, and how can we make them better, looking at the limitations and the powers that they have. So this gives us guidelines on designing further models, that gives us some intuition about why it happens that we see happen empirically. Yes, and it just helps us better understand how we can learn with structured inputs such as graphs, molecules, and collections of items.